Hello everybody, welcome to this session. Qui parle français ici? Who is speaking French here? Some people are speaking French? No? I'm super surprised. Ah, thank you, you are. So this talk is in English, not in French, but in French, English, okay? That will be okay. First of all, I need to do something super important. Oops, not this. I need to take a picture, and you need to smile, right? All the time, smile. Yeah, good. And here, because you are jealous, I think. Yeah, very good. Did you smile? Yeah, you did. Okay, we are going to speak about advanced search for your legacy application. And actually, this talk is based on my own experience when I was working for the French customs. And I had exactly this problem. I had an application running using a MySQL database or a Postgres database, I don't remember exactly. I had to add a search engine on top of it for reasons that I'm going to explain. And this is basically the story I'm going to speak about today. So during the talk, you can, if you have internet connection, you can connect to slido.com and use this hashtag Elastic, and you can ask every question that you want. You can vote for the question for the other attendees. And at the end of the talk, if I have enough time, I will answer the questions. And if I don't, I will answer the question on Twitter. Right? So just go to slido.com, Elastic, and then ask for your questions. So some words about Elastic. Elastic is the company behind the product which is well known, which is Elasticsearch. This is the thing that we are going to cover today. So Elasticsearch basically is a search engine where you send JSON documents in it using a REST interface, and then you are able to retrieve your data, to search for it. You are able to scale horizontally and deal with petabytes of data, what have you. So it's extremely fast, extremely powerful, all that stuff. We are also providing in the open source field Kibana. So Kibana is a UI that you put on top of Elasticsearch, and then you are able to visualize the data that you have indexed. And you can also use Kibana for running some basic curl commands. And I'm going to use Kibana for that purpose today. We have also something to ingest your data inside Elasticsearch. This is also open source, so you have bits. Bits are agents that you put on your machines. If you want to deal with logs, for example, you can use FileBit. It's going to stream your logs to Elasticsearch where they will be indexed. If you want to collect data coming from the network card, then you can use Packetbit. Packetbit is like running Wireshark on your network card and then index whatever query request that you can see on the network layer. MetricBit also is about metrics on the platform and metrics about some application that we know. Or a lot of community bits as well. In MetricBit, you have also things about Docker. If you want to have metrics about your Docker containers, then you can use MetricBit as well. Logstash is an ETL. You basically extract data from a source. You transform the data on the fly. It means that you can enrich the data. If you have an IP address with a geo-IP filter in Logstash, you can extract from the IP address the geolocation point and then display on a map in Kibana where your users are coming from. All that stuff. You can do many things, transform into JSON documents, and then export and load to Elasticsearch or to any other destination. So this is totally the purpose of the ETL tool like Logstash. All that is open source, and then as a company, we are extending the stack with a plugin that you can put on top of the stack, which means that you can remove it anytime. We don't have an enterprise version of the open source stack. So XPack is bringing you security, alerting, monitoring of the stack, some reporting, graph exploration of the data that you have indexed inside Elasticsearch, and also machine learning. Machine learning is a super cool feature where when you index time series data, it will compute automatically a model out of it, and then it will compare the new data that is coming from you inside your system with this model that has been computed. And anytime you have a value which is going outside the model, then it's an error, an alert, or a normal pattern. So this is something that machine learning can detect. So we have a basic license for XPack, which contains some features, not machine learning. And the basic license is free, so for example, you have monitoring inside it, and you have some advanced tools in Kibana. So I will encourage you to use XPack at least basic license, which is free. We are providing all that as a service, either in the cloud, on Google Cloud Platform, or on AWS. You have just to choose, or if you want to have all that managed by yourself, but within your company, you can use the cloud enterprise that we have. Okay, that's all for the commercial part, but I need to do some commercial, right, to pay my ticket. So this is the view of the cloud by Elastic. Oh yeah, but I don't have it. Oh, I have internet connection. Internet is back. Cool. Okay, so you can do something like this. I want to create a cluster. Then I can choose the size of my cluster. I can choose if I want to run it on the Google Cloud Platform and whatever number of data centers you want to have the data copied on, all that stuff. And everything is managed for you. You don't have to worry about that. Okay, I'm David Pilato. I am known as Dadounet on Twitter. I'm living in France, as I said. So after the session, I will answer to questions here on my Twitter account, and also I will share the repository that I'm going to use with a tweet. If you can tweet and use Elasticsearch hashtag or something like this, take pictures, that's super good for my income. The more tweet I have, the more income I have, so please tweet. I joined Elastic in 2013. And I have been working at the beginning on the Elasticsearch project itself. So this is the Elasticsearch repository. I have been contributing a lot on the open source plugins that we have for discovery, snapshot restore, that kind of stuff. So, starting from the beginning of this year, I moved to a more evangelist position. So you can see that my number of commits has decreased a lot. I'm still doing some code during the summer. This is what you can see here. Okay, the repository I'm going to use today is this one. So under my account, Dadounet Legacy Search. So if you want to replay everything that I'm going to show you today at home, you just have to look at this repository and switch to the different branches. All the time you have a README file, if the Wi-Fi works. If not, no worries. Yes. So in the README file, you have all the instructions that you have to follow to run the branch. And what I'm going to explain today is how I'm going to switch from one branch to another, actually, but doing all that live. So what you have to do is just to compare one branch with the other, and you will get all the details about all the steps. Cool. I'm done with that? Yes, I'm done. So we have an application running here. So my application is already running here no, it's not here, sorry, it's here. So it's running from IntelliJ here. It's a Java application. I hope that you all guys are writing and understanding Java. Yes, I guess. So my application is managing entities which are persons. I hope you can see that. So here I have a bin person where I have the name of the person, the date of birth, the gender, number of children, and then some marketing data that I'm not going to use, an address like a country, city, location point with latitude and longitude. Okay, so this is my data set for now. I'm using Hibernate behind the scene, and Hibernate is generating the database for me. So I have here a table for person, a table for address, and a table for marketing. Right. And I wrote some code that I'm going to show you just after. That code is helping me to search within the data that I have stored in the database. So here, this is my basic application. I have a Google-like search feature here, where I can search for people. I have nothing yet indexed, injected in the database. So what I need to do, I need to inject some random data. So behind the scene, I'm generated random people. And yeah, you can see the injection here, which is happening. And if I search now for them, I can see that I have some people coming. Maybe I need to zoom in again. I hope you can see that from the back. That's okay? Okay. So I can search inside my dataset. I can search for different fields, like Joe, for example. Okay. Living, I don't know, in Paris. Okay. So it's working very well. I have also the advanced search here, where I can specifically search within the name field, the country field, or the city field. So I can search for Joe, living in France, living in Paris. Okay? Basic search feature that I have. So let's have a look at the implementation. If I'm looking for the first one, the find like Google method. So from the interface, can you see it from the background? Yeah? Sure? Okay. No. Okay. I was pretty sure it was not enough. Okay, so I'm going to increase that. 24 maybe. Okay. So here I have this find like Google method where I'm getting from the interface a query that the user is entering, and I'm using Hibernate, as I said, to generate the query here. So what I'm doing, basically, I'm building a like person strategy query, right? And I'm going to do a join in the address table because I have some data available in the address table. And then I'm searching for what the user has entered in the name field, or in the address.country field, or in the address.city field. Basically, this is what is happening behind the scene. And if I look at the advanced search that we have, this is super similar. From the interface, I'm getting the name field, the country field, or the city field. So this is what the user has entered. And if I have anything in name, then I'm using the same like person strategy, but specifically on the name field, or on the address.country field, or address.city field. Okay? So this is what we have. Okay, what's wrong? Nothing. Everything is working. We don't have any issue, right? Okay. So let's use the search engine a bit more. So Joe Smith, okay, working very well. Let's search for Smith, yes. Joe. Oh, I don't have any Smith Joe in my database. I know I have one Joe Smith, right? But as you see, the way the implementation is done, I should maybe broke the sentence as every single space and try to combine all the thing, but yeah, it's not like this by default. Okay, I can search in the country field. France, okay. Oh, this is bad. Can you see something bad here in the result set? Okay, sensitive, no, it's not the issue. Yeah, Italy, but that's not my concern. My concern is that France Gall, so she's a famous singer. Who knows France Gall here? No one? Oh, okay. Okay, I love you. So France Gall actually has France in the name. I feel like that this record is much more relevant than the other ones, right? We have many people living in France. This is not that relevant, but France Gall should be on the top of the list, right? She's not. Okay, we are speaking about relevancy here. I have only 10,000 records, maybe I can deal with that, but if I have millions of records, how I can find the most relevant information for my use case? Like when you are using Google, probably you are not going on the page 10 or 11 or 12 of the records. You expect to have the most relevant information on the top of the list, on the top of the first page, right? So we have this issue. This is something we need to fix. Let's search for G-Smooth. Oh, I can't deal with typos, right? So I have another issue. So to fix all that, I want to use a real search engine, like Elasticsearch, which is the best one, but I'm biased. I'm working at Elastic. The problem is how you are going to send the data that exists in the database or exists in your application to Elasticsearch. You can have multiple strategies for that. One of the strategies is to use an ETL. So you can use Talend, you can use Mule ESB, you can use Logstash if you wish. and every 5 minutes run a job that collects the data from the database, transform to JSON, and send that to Elasticsearch. But it's every 5 minutes or 10 minutes, I don't know. Which means that when my user click on the save button in my application, he will have to wait for 5 minutes that the records become searchable. So we are not in real time. For some use case, it's not a problem, but for my use case, it was. But then how you deal with updates? I mean, okay, I am updating a record, what I'm doing in the next 5 minutes. I am going to select star from the table and get back again all the data set and reindex everything? Or maybe I need to add a technical field saying that I have updated something and then sort by this field or filter by this field, I don't know. It makes the things a bit more complicated. One thing which is more complex sorry, is to deal with deletes. How do you deal with deletes? When you are going to run your select star from table, you have to know that something which is not coming back has to be deleted, which is super hard, right? It's not coming back, but I have to delete something that I don't know. Okay. So maybe you need to have a technical table, or maybe use triggers, but you are going to complexify, I think, your infrastructure. So to me, the best possible way to do that is to modify the application layer, if you can, if you have access to the application, and within the same transaction, which is generating the data to the database, send the data to Elasticsearch. And this is what we are going to do now. Okay, make sense so far? Cool. You understand my French English? Yes. Okay, cool. Thank you. So, the first thing I need to do is to add Elasticsearch on my project. So I'm going to here add Elasticsearch. I'm using the latest version that we released recently, so we might have some bugs. I'm going to use the high-level client. Why did I say that? This is the GA version. No, we don't have any bugs. You can use that in production. No worries. Okay, so I have added my Elasticsearch client here. The first thing I need to do is to go to my save method here. So this is the same method that I'm calling to save an entity in Hibernate here. So this is where I'm doing the persistence. So what I want to do here in the same transaction, I want to call Elasticsearch DAO class, and I want to save my person object. Okay, we need to create that. So that will be final Elasticsearch DAO class. I'm sorry. I need to create this class, DAO package. Okay. I'm using here a framework named Restix. Restix is like Spring Boot, but less known. So I can annotate this as a component, so I will benefit automatically from injection. So here I can inject it in my constructor. Okay, so it's here. So I have now my Elasticsearch DAO instance. I need to implement the save method. So I want to save an object inside Elasticsearch. What I need to have to do that, I need first to have an access to my REST client. So I need to create instance of the REST high-level client, and let's call that REST client. I'm going to initialize that in the constructor. So some way to initialize this. So what I'm saying here, I'm building a new REST high-level client, and basically I'm telling that it will connect to an Elasticsearch cluster running on this machine on this port by default, which are the default values of Elasticsearch when you start Elasticsearch. Okay. So I have a client. I need something else. I need a way to transform my bins into JSON documents, because Elasticsearch only speaks JSON. So you need to send JSON documents. To do that, I'm going to use Jackson, the library, which is super nice. And Jackson is providing an object mapper, which I already have in the RESTX framework. So I'm just going to inject it here. Okay. So I have now my mapper and my Elasticsearch client. So first thing I need to do, I need to serialize my bin as a string or as bytes, whatever. Right. This can send an exception. So this is in bytes. Here I have basically. I don't care. Okay, this is happening all the time. I don't know why. So I have here in bytes object my JSON representation of my bin, right? With all the data inside, the country, all that stuff. I don't have to deal with the fact that I have multiple tables in my SQL implementation. I just want to index person. So I'm going to send person. Then with my clients, I can index. I need to provide an index request. And I want to index inside what we call an index. So Elasticsearch is multi-tenancy, so you can have multiple indices for multiple purposes. This is the type of the document. With the type, you have a notion of the schema. And I need an ID. So I'm going to get the ID that Hibernate has generated, but as a string. And then I need to provide the JSON document itself, so which are our bytes. And this is JSON content. Okay. So basically, with those two lines, I'm able to send something to Elasticsearch to be indexed, right? Not super hard to implement. Let's compile that. Okay. I'm always missing this one. Okay. Let's do it again. So now I have a more serious problem that I have to deal with, right? While I'm communicating with Elasticsearch, maybe something can go wrong, right? So what should I do in that case? So I'm going to write some pseudocode to explain what you can do. This is pseudocode because this is not exactly what you will write, but it will give you an idea. So maybe what you want to do is to roll back the transaction and exit, right? I don't want that whatever I save in the database is stored in the database. Okay, so I can roll back. The issue here, and that was the case for my use case in the French customs, for the French customs, I said that anytime my user click on the save button and I'm able to save it on the database, then I don't care about whatever will happen with the search engine. This is less important for my use case. I want to store the data. So I was saying something like, okay, let's log and said, Houston, we have a problem. And then the admin team will have to deal with that. I did not print that in the logs, but I sent actually the documents to a message queue system, like a dead letter queue, how do you call that? Dead letter queue, where I was putting all the errors, and then I was able to replay all the things later, right? So that was what I was doing. So this is compiling this time. Let me show you how you can implement the same thing for the delete operation. I told you that it can be hard to implement if you are using an ETL, but actually if you are using this strategy, you can just create here a delete operation, knowing the ID of the document. Let's do that. Create method delete, yes. So this is the ID. What I need to do to delete a document, I need to call the delete operation with a delete request. What is the index name? Person, the type, person, and the ID, the ID. Okay? And I'm done for this. Well, what did I do? Okay. So, I have my, everything is set. What I need to do now is to restart the application. But first, I need to start Elasticsearch. So I have here the version 6.0 of Elasticsearch, nothing really fancy. I just need to provide a JVM, and that's all, and then I can just run Elasticsearch. I don't have to install anything. There is no database or what have you behind. Everything is stored locally on the disk. So Elasticsearch is starting, and we can see here that Elasticsearch is listening on that port. So the port I mentioned at the beginning. And then I'm going to start as well here. I have Kibana, because I'm going to play with Kibana a bit. So nothing specific to see. Just starting Kibana. Kibana is going to connect to the local cluster. And then I can open Kibana here. So this is my Kibana. And in the dev tool, what I can say, I can run some curl command, but more easy to type. So here I can just check that, okay, my Elasticsearch is running and I'm connected to my Elasticsearch, so everything is okay. For now, I don't have any index name person, so I don't have any data. So what I'm going to do is I'm going to restart the application again. Okay. No, you can ask now if you wish. So creating an index, it just creates storage where you are going to index your document in. But then if the question is what it's going to happen when you index a document, which is another question. So when you index a document, it's going to index every single field that you have. So it will create an inverted index inside Lucene. I don't know if you know Lucene, so this is what we are using behind the scene, Apache Lucene. And yeah, so this is basically what we are doing. So it's started. So let's reinject, I'm going to start smaller, 1,000 documents. So we can see that the rate is not that good. We were around 120, something like this, maybe 150, and now we have only 24 documents per second, so that's bad, I would say. But okay, let's see. So I have my documents coming. Can I search? So I can simply search for everything. So this is the typical result that you can have. That's bad on the screen. For example, this is a JSON representation of the document that I sent to Elasticsearch, right? So you have the name, date of birth, gender, marketing data, the address, everything is inside, right? And so Elasticsearch is indexing all the fields like this, okay? If we look again at, so it's basically working, but we are still using the database for search, right? We are still using the same SQL queries that we made before. So we need to change that. And to change that, we are going to modify our code a bit. So here, in the person service, instead of searching using the database, I'm going to remove all that code, and I'm going to search using Elasticsearch now. So what I need to do, I need to provide what we call a query builder. So that will be our query. And I'm going to say that if I have nothing entered by the user, then the query I want to build is what we call, it's what we call a query, match all query. Match all query means give me everything that you have, okay? If the user has entered something, I want to build a query, which is another one, query builders. This is the multi-match query that I'm going to use. What the user is searching for, Q, okay? In which field you want to search this value? I can say I want to search within the name field. I want to search within the address.country. And I want to search within the address.city field. And everything is indexed, which means that I can search also in the gender field if I wish. Why not? Okay, so I have my query now. So let's call Elasticsearch Geo. We need to create a search method where we are going to pass the query. And I want to show you how you can deal with pagination. So basically I'm going to pass from the front and the from and size parameter if you need. Let's create this. So this is a query from and size. So we need to implement that part now. So I'm going to use the client again. This time I'm going to call the search method, and I need to create a new search request. I'm going to search within only one index, so inside the index person. Then I need to provide a search, a new search source builder here to provide the parameters that I need. So I want to search for a given query. So this is the query I built before. And pagination is super easy. You just have to pass from and size parameter. Everything is out of the box. Okay. There is some noise. What can happen? Exception probably? Yes. Okay. This is a response object, and I'm going. Yes. I'm going to send that response object back here. Okay, so I'm able to run a query now here, so I have it here. So what I'm going to do, I'm just going to take that response, and my application is not that legacy. I'm not using struts or servlets or what have you. I'm using AngularJS in the front end, so it speaks already JSON, so I'm just going to send the JSON document back to the front end, and that's all. Okay. So it's done for this part, for the à la Google search. Let's do the same thing for the advanced search, and I promise that I'm going to type super fast. Like this. Okay. So this time, if I have nothing in name and I have nothing in country and then I have nothing in city, then it means that the user is searching for everything, again, match all. But if in the other case, I'm going to build a Boolean query, and if the user has entered something within the name field, then it must match on the name field. If the user has entered anything in the country field, then it must match on the address of country field. Okay? That's easy to understand. And then I'm calling exactly the same method again. So let's compile that. And probably I need to restart at some point. Yes. Oh, I did that already. So restart, it's here. So now I will be using Elasticsearch for search. Okay, done. So let's search again. So this is the match all query now. Okay. If I search for Joe, it does not work. It was working, but it does not work as it was working previously. But Joe is working well. Joe, the full term, is working well. We are going to understand what is happening. Joe Smith, okay. Oh, Smith, yes. Joe? Yeah, we have Smith Joe now, right? Okay. I can search for a gender, right? I can search for a country. Look, France gal is on the top of the list now, right? It's more relevant for my use case than the other data, so I'm super happy with that. What about the advanced search? Joe, so the full, the part of the term is not working, but the full term is working. France and Paris. Okay, so we need to understand what is happening. Yes, let's do again here. Just something. G does not work, right? G E E. So with typos, it does not work yet. So we will see that later. Before fixing the search part, I want to fix something else, right? So I have this impression that Elasticsearch is slowing down my process. right? 28 documents per second instead of 150. It's not super good. So the reason for this is that we are indexing documents one by one inside Elasticsearch. So every time we are calling index here, we are making a single HTTP request to Elasticsearch and then get back. Request, get back. There is a smarter way to do all that, is to use what we call the bulk processor. So the bulk processor is using what we call the bulk API behind the scene. I'm going to explain all that. Just let's do that. Okay. So what it does, basically, I'm going to add some requests within the bulk processor. And what this class is doing, every 10,000 actions, it will flush the bulk to Elasticsearch in one request. It will be much more efficient. And even though I don't have 10,000 documents within my bulk, then every 5 seconds, I will flush the bulk, whatever the number of documents I have. Okay, this is basically what is happening. So here, instead of calling directly the index operation, I'm going to call the bulk processor, and I'm going to add this request operation inside. And same for delete. I can add the delete request within the bulk. Okay? So let's compile that and check that it's working. Okay, no errors, that's okay. Before restarting and seeing the effect of that, I want to understand what was wrong with my search here when I was searching for GO. Okay? To explain that, I need to explain that Elasticsearch comes with a default mapping. So there is a schema which is guessed automatically by Elasticsearch anytime you send a first document. And maybe Elasticsearch is not doing the right decision for your use case. So here, this is typically the default mapping that Elasticsearch has generated. So he found that there is within my person index, there is an address.city field, and it's using the default text type here for this field. More than that, it's using what we call a default analyzer behind the scene. And I'm going to explain what the analyzer is doing at index time. So let's say that you have to index Joe Smith. To index that and to build the inverted index, you need to process that sentence, that string, to an analyzer. So if I'm using the standard analyzer here, behind the scene, this is what is generated in the inverted index. 2 terms, Joe and Smith. And when I'm searching for Joe, using, for example, the same analyzer, Joe is producing another token, which is GO. And GO is not GOE. That's the reason it does not match. Right? I can't find the same term in the inverted index. If I'm searching for GOE, then it's producing GOE, which is available in the inverted index. Okay? So that's the reason it matches when you have the full term, and it does not match when you don't have the full term. So how we can deal with that? We can define our own analyzer. I think I won't have enough time to explain all the details, but basically, I'm creating a new index here named test, and I'm providing my own analyzer. The name is the n-gram analyzer, and I'm using a tokenizer, n-gram tokenizer, that I define here. And this n-gram tokenizer is of type edge n-gram. And I'm going to explain what it does with an example. So when, I'm going to put that on the top, when I'm analyzing this same content with the n-gram analyzer this time, this is what is produced by the analyzer. So it will produce G, GO, GOE, S, SM, etc., etc., which means that we are going to store that in the inverted index. So when we will search for GO, like this, with a simple analyzer, simple, just lowercase the thing, that's all. So GO, I will be able to find it in the inverted index. So I will be able to retrieve my documents. Okay? So we need now to apply this strategy to our project. So you can create the analyzer and the settings by yourself by hand, by running queries like I did, or otherwise you can use open source project that I published, which name is Beyonder. And with Beyonder, it gives you an access to a class named Elasticsearch Beyonder that you can start on existing clients. I need the low-level client here. I can have an exception. Okay. So when Beyonder starts, it's going to look within the class path if you have a resource directory named Elasticsearch by convention. You can change that. And by default, if you have another resource inside, another directory, that will be the index name. So when Beyonder starts, it will create here an index named person. If I want to provide settings, then inside this directory, I need to add a underscore settings.json file. And here I'm going to provide the settings that I mentioned before, so my analyzer. Okay? So Beyonder is going to create an index with those settings. And then, if I create a new file named person.json, which is the type, then I can provide a specific mapping. And I'm going to explain a bit what is going to happen with this specific mapping that I'm going to set. So I will tell Elasticsearch that when you have a value in the name field, then it's always using the same strategy that we have seen. So the standard analyzer, it's always a type text, so we are not changing anything here. But at index time, you are going to copy the content of this field inside a new field named full text. And full text is generated at index time. And full text here is also a type text, so I want to run full text search on it. But I'm using this time the ngram analyzer that I mentioned before. Okay? This is the strategy. For address.city, same. By default, I'm using the text field, the text type, and I'm not setting any analyzer, so I'm using the standard analyzer. I'm going to copy these contents at index time to full text as well. Okay? But I'm going to do also something else. I'm going to generate at index time a new field named address.city.autocomplete. And this time, I will apply the ngram strategy on this specific field. Okay? And I will also generate an address.city.ags field, which is of type keyword, which means that I'm not going to use any analyzer behind the scene. I'm just going to index the document as is. It will be helpful to do sorting or aggregation that I'm going to show you. So I'm doing the same thing for country and all the other fields. And by the way, I'm saying also that location is now a geopoint and not only a float that Elasticsearch probably had guessed before. So I need to restart, but before restarting, I need to remove my index. Otherwise, Beyonder will refuse to create it. Let's restart in debug now. Hopefully, this is going to start. I have 15 minutes, right? Yes, I think so. So rock and roll means everything is okay. First, we are going to reindex some data now. Let's see if I can reindex 10,000 documents, maybe. Okay, so it's better. It's better, much better. We'll see at the end. So for now, if I'm searching, I did not fix anything. Why this? Because I'm still searching in the name field, and the name field is using the standard analyzer that I mentioned before. So I need to change a bit my code. Where is it? Super tiny here. It's here. So here, instead of searching in the name field, gender field, address.country, address.city, I'm just going to search in the full text field. And what I can do as well, I can say to Elasticsearch, okay, if you find what the user is looking for in the name field, then it's much more relevant for my use case. So I want to boost the result by a factor 3. So it means that it's the score that you are going to compute. If you hit on the name field, it's really much more important for my use case. Okay? So I can control the relevancy with this. So let's try it. If I search now for Joe, G, O, E, okay, it's working very well. So you can see that the first term of the list are Joe, yeah, of course. If I search for France, François, oh, France, you see, boost by a factor 3, so it's on the top of the list always, right? Okay, so that's okay. If I search here for G, we did not fix here yet the advanced part. So let's fix it. Instead of searching in the name field, which is using the default analysis strategy that we mentioned, we can search within the field autocomplete, which is generated at index time now. Okay, let's compile that. Okay, so let's search for G, O, living in France, living in Paris. Okay, so I'm back with more features, but I'm back if you compare to what we had before. So I have often this question, okay, the rate is good now, it's almost what we had with the database. I had sometimes this question, are you going to slow down the database with your Elasticsearch process? So let's do a simple exercise here. In the save method, I'm going to remove the call to the database, and I'm just going to call Elasticsearch. Right? I'm just going to index inside Elasticsearch. So I will measure how fast I can be with Elasticsearch. Because I'm not calling Hibernate anymore, I'm going to remove this because I'm not generating the ID anymore. So I'm going to let Elasticsearch generate the ID for me. So let's compile that. And see. So 10,000 documents, done. Okay, so let's index a bit more, maybe 1 million documents now. So it's much, much, much faster, right? Elasticsearch is not going to slow down your process, right? It can index very efficiently. And what is cool with a search engine is that you can actually search within some milliseconds. If I'm searching for Joe, Smith, Paris, what have you, right? This is a search engine. This is built for that, okay? So let's continue. You can see the number of documents increasing here, right? It's fast. Okay, can we do something more? Yes. What we can do is to build also what we call aggregation. I want to understand the result set that I have. So for that, I'm going to build 2 aggregations. The first one is a terms aggregation. It's going to give me the top 10 values that I have within a field. So here, this is the name of the aggregation, but I'm going to compute the top 10 values on the address.country.ag. So here, basically, I want the top 10 countries I have in my result set. Okay? And I'm going to build another aggregation, which is this time a date histogram on the field date of birth. And I want to compute a bucket every single year. And I want to understand how many documents I have for every single year. Okay? So this is what I'm doing. I'm cheating again because I have already everything in the interface. So if I'm searching again, so I finished my injection, right? It's over. Right. So I can see, I'm going to zoom out. I can see that for my 1,020,000 documents, I have that number of documents in Germany, Italy, France, England, and that number. So this is the result of the terms aggregation, and this is the result of the date histogram aggregation that we have. So of course I can search, okay? So this is the distribution of my Joe broken by country, broken by a date, what have you. So you can do a lot of things super fancy like this. I have time probably to do something else. You can also implement what we call the faceted navigation pattern, which means that when a user clicks on France, you want to filter all the results for the people living in France. Okay? So here I want to see, for example, all the Joe living in France. Obviously, it's not the case yet, because I did not implement that. But let me show you exactly what you have to do in that case. So maybe you notice that in the search feature method that I have coming from the interface a filter by country and a filter by date that I'm not using. So what I'm going to do here, I'm going to add this. I'm going to say, if you have anything in the filter by country or anything in the filter by date, then do a Boolean query and add inside the query that we built before, and it must match this query. But then if you have anything in the filter by country, then filter the result set on the address.country.ags with the value of the country, so France, or here, for the date, I'm building a range query between two dates, which is the date that we selected, plus 10 years. Basically, this is what we are doing. So let's compile that. So if I'm searching again now for Joe living in France, so I have Joe, only the Joe living in France. And in the 60s, okay, I have only Joe living in France in the 60s, right? I can remove that, I can search all the 60s in England, I don't know, yeah, Joe living. Okay? So this is the pattern of faceted navigation. And we can do more. Do you want more? Yeah, okay. I'm doing that myself, okay. So we can build multiple levels of aggregations. You can say, I want to build the first level of aggregation, which is I want to break by country. But then for every single country, I want to break again with a data histogram by year, so every 10 years. And then for every 10 years of buckets, I want to compute the average number of children that I have. Okay? So this is basically what I'm doing. Let me change some HTML code. I'm super good at HTML. I can remove comments. Okay, so I should have a new button, compute. So now this is the result of this aggregation. You have the number broken by country, then broken per 10 years, and then for every single 10 years, the average number of children that you have. And of course, you can search for Joe inside this data set and understand what you have within your result set, okay? Super powerful. One last thing we need to deal with is the typo, right? Super hard to implement. I mean, in SQL. Here, what I need to do, I'm going to say, okay, you are going to search within those two fields, but I'm allowing you a fuzziness factor, which means that you can modify a letter, you can remove a letter, or add a letter, for example, and that will still work. So let's do that. So it's hard, right, to implement. So multiple letters, I'm going to cover that. Okay, so gsmoth. Okay, so I have my gsmoth now. Okay? Multiple letters, I can do 2. Okay, so I can change now 2 letters if I wish. Not more than that, because after that, if you search for Smith, you are going to get back elephant, which has no meaning. So here, if I search for here, okay, I have Joe, something, Kim. So, you know, yeah, you see it's not ideal. So better than that, you have the auto here value, which is definitely better. If you use auto, it depends on the size of the term that you are searching for. So if you have a small term, it will be the exact term. If you have longer term, that will be 1. And then if you have big term, it will be 2, automatically, based on that. Okay, one last word. Once you have indexed, oh, yeah, by the way, I can do that in the advanced search as well. I can just add the fuzziness factor here. So that's the same thing. Okay. So once you have done that, we have 1 million and blah, blah, blah documents inside Elasticsearch. You can use Kibana for what is built for. You can search within your index person, for example, and say, I want to search from 1940 to 2010. Okay. So I have my 1 million hits. So this is the result of a date histogram that we have seen, of course. I can search inside for Joe. Okay, I can select fields, what have you. And then I can build some nice visualization using this tool. And then I can put all those visualizations on a dashboard. And basically, this is what I did. We'll see if I have the internet connection or not. It depends. We'll see. So here, we have a map. So we have internet connection. So this is the distribution of my documents. So the result of the aggregation that I mentioned. Here, the geolocation point that I'm using, so I can display everything on the map. So I can obviously search for my Joe. Okay, so this is the distribution of my Joe. I can understand all that. And if I want to search for Joe who are women, I can just navigate and filter for all women born in the 70s, maybe living in, where is France? No, Italy. Oh, sorry. I want to remove Italy. I want France. France. Okay, living in Cergy. Cergy is the city where I'm coming from. And so it's a random pattern, you can see, right? This. Which is cool. You can also select here, I want to see people living in this area, for example. Okay. And I have the result set. So I built Mythic. I don't know if you know Mythic, but yeah, time over. Yeah, I have 1 minute. No? No, I have 1 minute left. Don't steal my minute, please. And I can do exactly the opposite. Okay? I'm done. Thank you for listening. And if I have questions, so I will answer because I'm running out of time. I will answer to the question on Twitter. And so I'm going to tweet here the session. Thank you so much.